Okay, so good evening everyone. My name is Athra Gulwale, currently studying at Ramdev Baba University. My branch is Computer Science and Engineering. Today we will learn the topic Deutsch algorithm. Before moving to our main topic, we would like to discuss about few terms like functions. Here, let's consider a function is giving 0, 1 as input bit and having the output bit as 0, 1. We know that there are many types of function, but in Deutsch algorithm we use only two types of function. First one is balance function and the second one is a constant function. Before balance and constant function, we will like to take information about Boolean functions. Boolean functions are defined as f of x where the x belongs to the range 0 to 1. A Boolean function is an expression form containing binary variables and its answer will also shown in the binary. Boolean function's goal is to determine whether the function is constant or balanced. Constant function. Constant function is a function which produces the same output regardless of value of input of x. Such a function is called as a constant function. Here I have also given some example which includes test inputs as here f of 1 is giving a output as 7, f of minus 2 is also giving the output as 7, f of minus 10 is also giving the output of 7 and f of 10,000 also giving the output of 7 and so on. Now, balance function. A balance function is a function where the number of outputs of 1 and 0 are equal over all possible inputs. In which algorithm we mostly use this balance function. For example, we know that in digital communication system like Wi-Fi, Ethernet, etc., binary data is transmitted over the network. The balance function are often used to ensure the signal has equal numbers of zeros and ones. Here we can see a clear comparison between balance function and a constant function. Balance function in here x is used as input and f of x is working as the output. Here we can see a clear result of a balance function in which where the output is giving 1 and 0 as balanced one, and in the constant function regardless of any input in the x, f of x is giving only one constant value, either 0 or 1. Now we will move on to our next topic, which are just important notes. Classical computer. Classical computer needs only two query of the function, whereas the quantum computer needs only one query of function. But in quantum computer, all operations should be reversible. Here is a graphical representation of how the function works. Now we will learn about the concept of quantum oracles and phase oracles. Quantum oracle. We know that quantum oracles are just used to make quantum operation reversible. Here I have given the graphical representation of quantum oracle in which x is used as input bit and y is used as a target bit. Here I have also given the equation of quantum oracle which includes the XOR gate and having the output as y XOR of f of x. Now we will move on to phase oracle. We know that phase oracle is used for flipping the phases. Here the circuit diagram of phase oracle and the equation required for phase oracle and the output which can be produced from the phase oracle system. Now, before moving to Deutsch algorithm, we need to learn some key concept regarding superposition. What is superposition? We know that superposition is a fundamental concept in quantum computing where the qubits can be in both 0 and 1 at the same time, unlike a classical bit, which is only one or the other. Superposition allows quantum computers to process many possibilities at once, making them much faster for certain tasks than classical computers. For example, think of flipping a coin whilst it's spinning in the air. It's both head or tails. That's the superposition. Only when it lands, when we measure, do we get one definite outcome. Now the interference. Interference is in quantum computing is how the quantum state amplitudes combine either by adding up or cancelling out just like waves. There are two types of interference. First one is constructive interference and the second one is destructive interference. In constructive interference, the amplitudes get added, which ultimately increases the probability, and in destructive interference the amplitude get cancelled, and which ultimately results into decrease in the probability. This helps quantum algorithm amplify the correct answer and suppress the wrong one. Interference is a topic that gives a quantum computer their problem solving power. By using it, they can zero in on the right answer faster than the classical computers. Now we will learn a Deutsch algorithm circuit diagram. In this circuit diagram, we can see there is a 2 qubit, 0 qubit, and another one is also 0 qubit, and these are the quantum initial quantum state. This one is initial quantum state, and other are first, second, third, and fourth respective quantum state. Here this x is showing Pauli's x gate. We can also call it as a quantum not gate, and h stands for Hadamard gate, and this is a quantum oracle. Now yes, we start with the initial quantum state, in which qubit 0 XOR with qubit 0, then the result will be 0 qubit. In last slide, we know that X denotes the Pauli X gate, also known as quantum NOT gate. It flips the state of the qubit, 1 qubit to 0 qubit, or 1 qubit 0 qubit to 1 qubit. After that, the first quantum state gives a 0 qubit XOR with 1 qubit, which result into 1 qubit. This initial state of initial quantum state is the starting point of the algorithm. Before applying any Hadamard gate, it sets up the system for creating a superposition and eventually using the quantum interference to extract whether the function is a constant or balanced. And here H represent Hadamard gate. It is used to create superposition state. Here the second constant state is giving the required equation, which can be also simplified as 1 by 2 of 0 qubit minus 1 qubit plus 10 qubit minus 11 qubit. Now after adding the quantum block oracle UF, it modifies the phase based on the function f of x. After that, the quantum oracle x qubit y qubit is equal to x qubit y XOR of f of x. At this point, the system is in superposition of all possible input combinations 0 and 1s to create the function f of x, and the second qubit is ready to record the result of f of x through the oracle in the next step. Now here it is a brief explanation of second quantum state. In this process, the Hadamard interfere with the result and collapse it into either, if it is a 0 qubit, then f of x is constant, and if there is 1 qubit, then f of x is balanced. Now the third quantum state can be also represented as a resulting state. After that, the it can be expanded form of the equation is given above. If f of x, if f of 0 is equal to f of 1, then third quantum state is equal to 1 by root 2 0 qubit plus 1 qubit. If f of 0 is equal to 0 and f of 1 is equal to 0. And if third quantum state is equal to 1 by root 2 minus 0 qubit minus 1 qubit, if f of 0 is equal to 1 and f of 1 is equal to 1. As a result, when f of 0 is equal to f of 1, then third quantum state is equal to plus minus 1 by root 2 of 0 qubit plus 1 qubit. And if f of 0 is not equal to f of 1, then the third quantum state is equal to 1 by root 2 of 0 qubit minus 1 qubit. If f of 0 is equal to 0 and f of 1 is equal to 1, then the third quantum state is equal to minus 1 by root 2 0 qubit minus 1 qubit, if f of 0 is equal to 1 and f of 1 is equal to 0. As a result, when f of 0 is not equal to f of 1, the third quantum state will be plus minus 1 by root 2 0 qubit minus 1 qubit. As a result, we get if f of 0 is equal to f of 1, the third quantum state is equal to plus minus 1 by root 2 of 0 qubit plus 1 qubit. And if 0 f of 0 not equal to f of 1, then the third quantum state will be plus minus 1 by root 2 of 0 qubit means 1 qubit. Also, we can represent it as a third quantum state is equal to plus minus of plus qubit and plus minus of minus qubit when f of 0 is not equal to f of 1. If 0 qubit, if we get 0 qubit, then f of x is constant, and if we get 1 qubit, then f of x is balanced. Now the result of Deutsch algorithm. If we measure 0, then the function is constant since f of 0 is equal to f of 1. And if we measure 1, then function is balanced since f of 0 is not equal to f of 1. The conclusion. Here we learn some key concepts such as functions, quantum oracles and phase oracles, superposition, interference, Deutsch algorithm, and circuit diagram, and a brief explanation. Deutsch algorithm shows that the quantum computing isn't just different, it's more powerful for certain problems. With just one evaluation, we can learn what would take a classical computer to. That's the essence of quantum advantage.